So what we are going to do is going to be much more of machine learning. Now, machine learning, as we all know, is much more of understanding the context than the three-line codes. Machine learning is not too much of writing plenty code. It can just be just one code, and then you are able to get your results. But it's like cutting a big tree. You have to take time to sharpen your axe. You can take days, weeks to sharpen the axe, so that when you come, it becomes easier to push down the bigger tree. So machine learning is not. If I show you some few examples now, it will amaze you, and then for you to realize that there isn't much of the work. So if all the script you are seeing on my on my screen right now, is everything here is nothing until we get to this last part. This is actually where the machine learning is all about, and you can see that there are just few of the codes there, and that's all. Just from here up to this place, there are just few codes that are there. But check all that has happened from the beginning all the way up to this last part. And so in most machine learning classes, what I've noticed over time is when you sit there, these codes, like I told you the last time, they are available. You only need to know what you are about and what you are doing. And so the codes will come naturally. When you know what you are looking for, if you are going to plot a heat map, you can just check a code for heat map. And you should know where you're supposed to place your data and where you are supposed to place this or place that where you are supposed to. That is the reason why we do tutorial in data science. If not, any other information is available online, but you may pick that and may not be able to understand anything there. So I don't like that approach where you just go into a data science class or machine learning class and the whole thing is just dumped on you. The codes are just dumped on you and you'll be following and clicking. Then you just click everything to the last part and you don't actually know what you have done. I don't like that approach at all. So in the office, I was supposed to do some teaching for 6 weeks, and that was Introduction to Bioinformatics. That class I had different people from different backgrounds, from different countries. I had a lot of problems with my colleagues because my colleagues said that I was only doing tutorials and I wasn't supposed to be teaching. That I'm just teaching the people A, B, C, and I said that's my understanding. I really don't like this approach. I've complained about it, and trust me, guys, I'm not going to follow that same approach with you guys. Just dump everything and then you don't know where to fix this, where to do this. It's not helping. Can you believe in KNUST they can use one day to teach you R? One day to teach you R. Yes.
Wow.
In fact, it's not one day. It's actually one lecture. Yeah, the day we went for the lecture on R, that was the day we also finished it. And I never understood R until I had to just develop a deliberate effort to do that. All this machine learning and everything, even today, I'm not sure we are going to finish with machine learning. It's not possible. Because people use like a whole year to learn machine learning, to do machine learning. Then you come and use, okay, enough of the long stories. Now, in machine learning, so I'm going to be talking about this, if you can see my vision quite clear. Is it clear? Can you all see my screen?
Yes.
All right.
Yes.
So I'm going to discuss this small note I have put here, and then before we get into the studio. So machine learning by nature, by its what is it definition, like we talked about the last time, is basically allowing the computer systems. When you talk of systems, we are talking about the program that people have written, the script, the codes that people have written, and then these codes are given to a machine. The machine here is the computer, and then the machine is able to use those particular codes to explicitly analyze data and draw conclusions. And you know, in all data science, like any other data or statistical data, we have two types of conclusions. We have inference, and then we have just the ordinary conclusion or the exploratory conclusion that we have. The inference is what is much more important. You can draw a conclusion and say that based on this and this and this and this could happen. That's machine learning. You are just given a system, a code, a script that you have written for a machine to do one or two things. And the machine is now following that particular script or code, and then to use it to be able to do whatever that you have access to do. And that's machine learning. Now, in doing machine learning, and I also want us to know one thing, machine learning is nothing but modeling. You are just going to develop a model. And what is a model? A model is simply, an abstract representation of actual data. Or you are trying to reduce the dimensions of data into into a more simplified way for people to understand. If you look at the whole of KNUST, 100,000 student population. The first years who have come, there are 12,000. If we look at all of them, how can we tell those who are going to get first class from now? How many of them are going to get second upper? How many of them will not pass? Definitely some of them will be sacked. So who and who can be sacked? That's what modeling is able to do. Some people can pick some parameters from these students and say that student A, B, C is likely to be sacked. And that's what the model is saying. How accurate is that model? We can measure it. We can find out whether what you have said, is it likely to happen or it will not happen? Then we can check for that. That's machine learning. Machine learning is about modeling, using different models. There are models that are linear, in which there is a direct relationship. So one part determines the other part. That's a linear model. We also have other models which are not direct. There's no direct relationship, even though there is a relationship. In banking system, they call it the third party kind of thing. So we are looking at a student performance, and we just look at, okay, what are the parameters to determine that somebody will be able to do well in a class? Maybe we just look at the way the person is attending lectures, whether the person comes on time, he leaves on time, he doesn't sleep in class, he does all his assignment and other things. That's just the basic ones that we all know. That's what will determine somebody to be able to pass. But trust me, there could be other ancillary values which we are not seeing, but they also play a role in whether somebody will be successful or not. And those ones, when you are doing a kind of model, that include things that are not directly, that you cannot see the direct relationship with the output. We call that kind of model logistic modeling, because you don't have the variables are not direct to the output. So it's about modeling. Machine learning is about modeling. So where you model things that have direct relationship, and you also model things that are having indirect relationship. Now, when we go from there, we are just looking at, there are various types of machine learning algorithms. Algorithm is simply a formula, like the way we have mathematical formulas written in our books. The formula of a circle is pi r squared. The formula of this is this and this. We have that. And then I have been taught how to do teaching. So there's something we call methodology. If we go into methodology, we can also explain how we came out with that formula, pi r squared. Now, when we are looking at algorithm, there are also a lot of formulas that machine learning are using. And there are types of those formulas or those algorithms. There are types. One is supervised. The supervised here means that you have a large data set that, I mean, has been labeled already. You pick all the students in KNUST, all of them have been labeled. So we know their height, we know their weight, we know where they are coming from, we know the school they have completed, we know their results, we know how much they made, where they did not pass well, where they passed well, and of course we also have their cumulated something. I've forgotten of that name, the thing they used to fill in primary school. So we have the labels of all this. We can use all of that label to be able to determine. For instance, if we pick their cumulative records from primary school and the person has been scoring, let's say, this, there's a likelihood that that person will also do well. So the labels are already there. Now, when we take those labels, we can now say that, okay, we are giving those labels to the machine, and we are saying that any person who has been able to was getting 80 and above from class 1, class 2, class 3 in all the subjects, and now, I mean, that person is likely to get first class. So when we have set that algorithm, like I was saying, when we have written that formula and we give it to the machine is now using that one to check for any other person that is coming. So when you now put anybody's information into the machine will tell you that this person will get first class, this person will get second class, this person will get this. And so in that kind of machine learning is what we call supervised, because the data points have already been labeled. So you can go around Kumasi and sample a lot of people like Ghana Police, and you come and say, okay, if the person has maybe this kind of hair, and the person has maybe is having something like a drug in his pocket, or is this and this and this, say that the person is a suspect. So anytime you blow in the data, you have already given a label. So immediately the machine sees those labels, the machine will simply say, okay, you said if I see this and this, I should say this, so I will say the same thing. That's what we call supervised learning. And in supervised learning, we are dealing with classifications. So we use that one to be able to classify people. So we can classify those who are short, can classify those who are obese, we can classify those who are tall, can classify those who are in these categories based on the labels you have given. So these are the people who are wearing red. Then the machine will classify it, because you have already given a description called red. So if you want the machine to now put the data in groups, it will classify them accordingly. Then apart from that, under supervised learning, we also use what we call regression, and we use forecasting. I actually have a video on forecasting, either in R or in Excel, how to be able to forecast what is going to happen. If you have a business, how is the business going to do in the next 2-3 years? You can actually do that. I have a video on R for that. I also have a video for that in Excel, and then both of them are there. So we use that to be able to forecast, like the weather pattern, those who do weather studies, and then the climate changes and whatsoever, and then systemic what systemologies and whatsoever for those who are able to predict whether there will be earthquake or not. They always use parameters, and they set all those parameters already, and then the machine is now using those parameters. Immediately, suppose those variables that have been described is being noticed, then the machine gives the warning that there will be an earthquake in this area, or this and this. Now we also have what we call, let me jump and say, unsupervised learning. In this case, the machine is using two type of algorithms. We have the clustering and we have the dimension reduction. Let me also explain that. In this case, the data points are not labeled. So for instance, we have all the characteristics of the data of all the students in KNUST, but we have not said that if somebody has scored A from class 1 up to now, the person is going to get first class. No, we have not said that. So you just give the data set like the way it is. You have not given any output. You have not said if this and this happen, this will happen. No, you just give the ordinary data. Now, what can the machine do? And you tell the machine that it should look at that and identify patterns. So what the machine is going to go there and say that, okay, these are the people who have scored A all the way from class 1 up to now. You put them in that. These are those who score BB. It will put them. And so that kind of analyzing data in machine learning is called unsupervised, because you haven't given them label. The machine is just the machine is not supervised to do the work. The machine is doing the work by itself. So and then it will just put them in that particular group, which we call clustering. Now there's also something called dimension reduction. That's why I put into bracket PCA. That's the you can use the PCA to be able to reduce people dimension. Okay, we can say that okay, anybody who is 2.5 1.2 meters, 1.3, 1.31, 1.2, we all put all of them in one category. So now we can do that, or we can say that okay, we want to remove all those who are 1 meter height, and all those who are 2 meters high, and leave only 1.5 to 1.8. So we have reduced the dimensions, into a particular category. So dimension reduction is also under unsupervised learning. So we also have semi-supervised. In that case, part of the data is labeled, the other part is not labeled, and you are using the labeled part to be able to label the unlabeled parts. So I have all students who I already know their characteristics. Then I put those characteristics in the machine. But now I'm going to bring different students. I have not measured their characteristics. Then I come to just give that to the machine to determine who they are. The machine will then use whatever information it was having already as a guide to be able to do to label the other students. And that's what we call semi-supervised. One part of the data is labeled, the other part is not labeled. Now, reinforced learning, very, very important. This is a regimented learning approach. This kind of approach is much more of like you have a data point that the relationship is not straight away. And then, but you still want to find out whether all the hidden information that are from one end, are they all joined together to be able to put to be able to determine the output. So you are kind of like regimenting the learning approaches. You are kind of like combining different different algorithm or outcomes, and then to be able to come out with a single output and then make a case from it. I'm going to throw more light on reinforced learning as we go down. Now, when we go to machine learning algorithms, the algorithms that I spoke about here, these are the types, the 4 general types of algorithms. But what are those algorithms? They are here. There's one like with the naive Bayes classifier algorithm. This one comes under supervised learning, and what does it do? It allows prediction. So if you are dealing with machine learning, if you are going to analyze your data using machine learning, you should be able to know which kind of algorithm you are using. And this question comes often, like in defense. So, for instance, I'm going to use classifier algorithm. Now, those who are going to analyze or those who are going to evaluate you will look at, okay, but was it a supervised learning or was it under classification? So if your machine learning was unsupervised and it was on classification, then you can use this particular approach. And what does that approach do? It means that whatever you are looking out for in that your data is for prediction. And what are you predicting? You are predicting a class. You want to predict the class or the group or the category. All right. So this particular bacteria is likely to be a bad one, or it's likely to be a pathogen. So it means it's going to be causing diseases. So you are able to predict. So you have, like those in microbiome studies are able to do that using this kind of classifier to classify all the bacteria who are pathogens and the non-pathogens by non-pathogenic bacteria or pathogenic virus or non-pathogenic strain or whatsoever. What it if you are going to do prediction. So it is based on a given set of features using probability. Predictions uses probability. Everywhere you have prediction, there is probability there. Now, the second method is the k-means clustering algorithm. This one uses distances. Unlike in the naive Bayes, this one you are using, you use this particular algorithm, supervised learning. And so you can see that if it is unsupervised, then we're talking about clustering. And so we're saying the like group data represented by the variable k distance. So for you have data, and we are looking at data points are. So the data points, are they close together or they are wide? So those that are closer together, then you put them at one point. For instance, in biology, we always say that in linkage disequilibrium, we always say that if you have alleles which are in locus that are, or in loci that are closer together, they are likely to be inherited together. This is one basic principle that is being used in GWAS and then the other learning. If you check on the human chromosome, the loci that are closer together, the alleles in it are likely to be inherited together. It's the same way we are dealing with here. So if you look at data, if you have your data and your data is being arranged, I'm going to come to data arrangement. And then it's arranged in such a way that those data points that have the same measurement, they are likely to be more similar. So we have that particular k distances. If you have done something like ancestry studies, it's the same way. For instance, that we get to know that there is a particular number we call centimorgan that you can set, and then you subject the person's DNA after you have done all the whatsoever, and then based on a particular distance, and then the distance, maybe the highest is 7 what is cm centimorgan. So that particular number becomes your k distances. So those people who might have the same measure is one. The k becomes the measure. Yes, we write that one, put k distance number here. You are what you are able to use to know that okay, those who fall within this measurement, or how closely or diverse they are, then you can put them together. Now another one is the support vector machine, and this algorithm works to build a model that assigns new values to a category or the order. So in this case, you have chosen one single value. For instance, you have a match of data points, height. So you have chosen, let's say, 2 meters. Then 2 meters become your central point. The machine look at anything that falls below 2 meters, it will put it one side. Anything that falls above 2 meters, it will put it on another side. And that's what anything that falls within 2, it will also put it on one side. It's going to use those values to be able to put all the data. So okay, you belong to this category, then to put it there. And you can see that it is what? A supervised learning and a classification, where you simply have a single metric that allow the machine to now be able to determine the other metrics. Now linear regression, we all know this. It's just a relationship between two variables, and we also use that in supervised learning. We have logistics regression, also a supervised learning, but here you are looking at, anytime you see logistics, you are just looking at two outcomes. And that's why in machine learning algorithms, when we go into the studio, you will see that I'll write there and I'll say family. I'll go and put binomial, family. I will not put anything there. When you say binomial, it means you are dealing with a supervised learning, but the outcome can just be two. Either present, absent, dead, alive, tall, short. You don't have like more than the two outcomes. That will no longer be probability. So you have the probability over here, 0 and then 1, to represent two different outcomes. And then that's logistic regression for you. Now, artificial neural network is reinforced learning. This is what I was trying to say. Now, you notice that you have a large number of interconnected processing elements. This uses the human brain. Before the human brain is able to produce an information, it has a lot of things. So that's where the word neuron comes from. So much neurons in the brain. We have to put a lot of information together to be able to produce an output. To say that, oh, no, what is smelling is rice. You see? So, or what I am seeing is a human being, but not a goat. That's artificial neural network. So you are having a lot of interconnected elements. So it's not only one, in biology, it's not only one allele or one SNP. No, I'm saying SNP, one allele that is responsible for height. Of all the traits that we always measure, one of the polygenic traits in the human body is height. So many genes come together to determine height. All right? So there are a lot of interconnected elements that you will have to be able to put all of them together before you can say that that is what has happened here. So how are you able to do that? That's why you have artificial neural network as part of machine learning. You build that and you see a lot of layers. You can see that, okay, this particular part is connected to this layer. And from there, this one is also connected to this. And from there, the output. So that's why in artificial neural network, you can see a lot of neurons at the back. Then as you go closer to the output, the layers are now reduced up to hidden layers and outliers, and then you have your output. So it's also like a model, but that model is not linear. There's a lot of interconnections that have to all be put for one to be able to say that, okay, this is the path I need to follow if I have to get this. Now, we also have others like decision trees that comes under supervised learning. Decision trees, I think we constructed one during data visualization. So I'm just saying that each node represents a test. So decision trees are they are very good when you are doing evolutionary studies. So you want to know whether what the Paulinus grandmother is from what is Scotland. So we can actually build what is it, a decision tree, and then or evolutionary tree, and we can trace that using machine learning. So it's going to print out the tree, and you can see what is it, how Paulina is connected to the mother, and how the mother is connected to the grandmother, and how the grandmother is connected to the great grandmother, and how the great grandmother is connected to another person, all the way up to whatever we are looking at. So several branches. We can also use that to be able to have different ways of coming out with something. So let's say we have a whole outcome on top there, and we are saying that, okay, if the person is tall, okay, then and what is it? So we are looking at two human beings here, or two outcomes here. Okay, one is tall, one is short. Then we branch to the tall person, and we are saying that if the height is below 1.6 meters, then we should branch to that particular branch. So when we get there, we find out if the person is fair or the person is black. If the person is fair, then we branch from that place, and then we go there and say if the person has red hair or doesn't have red hair. If the person have red hair, then we branch to that side. So we are getting up to where we can say that, okay, that person is an albino. All right. So we are just tracing a specific allele which is responsible for albinism. So we can pick the people and start following the decision tree, and then we are branching. We leave this branch, so you don't qualify. Then that branch is put elsewhere. Then you follow the other branch until this. We're also doing it in basic mathematics. If you can remember, factor tree. You see, then you come here, leave that, and then come here, leave that. What machine learning is much more of like, it's just mathematics. Now we also have random forest. This one is you are combining different multiple algorithms. So it's not only one. There are several algorithms that you are putting them together for an outcome. So it means that you can't use one single algorithm in this case to come out with your outcome. There are more of that. Don't worry about the codes and whatsoever. Those ones they are not anything difficult. Now the nearest neighbor, that's also supervised learning. That one is estimate how likely a data point is to be a member of one group. Nearest neighbor is not too different from support vector machine. It's not too different. Just that the nearest neighbor is also using like the k distance metrics to be able to know, okay, who is much closer in terms of similarity or in terms of diversity, and then to be able to put your data or to be able to classify your data based on the way you want it. The most important thing here is for us to know that if I'm dealing with supervised learning, these are the number of algorithms I need to use. And each algorithm, what is the outcome? Some of them are for prediction, and some of them are for classification, and some of them are for regression, some of them are for something else. Just know that and choose your algorithm accordingly. Okay, now there are major steps in data or major steps in machine learning. I think at this point, pay greater attention. The major steps in machine learning, first of all, we should be able to collect our data. Collecting data here is not like just going to the field to collect the data. I think I should have put there, understand the data. So understand the data is what we did previously, saying that, okay, when you have data at one point, there are some things that you need to do to understand the data well. If you guys can remember, there are some things you can do to be able to understand the data. First, you need to check the structure of the data, because that will give you some information. Check the dimensions, check the class, check the summary. All right, so when you do the summary, you see some columns are returning like NAs. It means there are some missing data there. You see, so those things is what we call like collecting the data. You are just trying to understand the data. Now, the next thing is data wrangling. Data wrangling. I mean, has any of you heard of data wrangling before?
No, please. No, please.
Data wrangling is like preparing. Come again?
No.
Okay. Data wrangling is, I am going to go it step by step to do that. But let me give you what data wrangling is all about. These are the major steps in machine learning. First, collecting data. I've just told that you need to understand the data. Check the structure, check this. Finished. You've understood your data that, hey, I have this. These are the number of columns I have. This column is named this. This column comes first. This one comes second. That's understanding the data. The structure, the positions of your variables, and what kind of variables are there, the entries and whatsoever. It tells you to also know which ones are factors, which ones are doubles, which ones are integers, which ones are numeric, and whatsoever. That's collecting your data. 2, data wrangling is actually the rich. People always confuse data wrangling with data cleaning. It's not the same. Data cleaning is just like you have some outliers and some missing data and some bad data there, some impurities in your data that you are removing, so you are cleaning them. But data wrangling is reshaping the data. It's much more of like data reshaping. You are going to there are a lot of things you need to some of the data points may be too abstruse. You need to normalize it. Some of the data must be kind of like outliers. You need to take them out. If not, they are going to affect you. For instance, we are going to measure and permit me to tell you this. This is one of the things that our finance ministers and whatsoever are so mischievous with in Ghana here. Data wrangling. If you are a data scientist and you don't pay attention to the data wrangling, you'll be given wrong report, invalid report. And let me give you one example of how we do it in our economy. In Ghana, we always say that our net or our balance of trade is 1. In economics, balance of trade 1 means that the number of items we are importing is the same as the number of items we are exporting. That's balance of trade. I'm just checking to see if the guys are around. Now, when you do that, but if your balance of trade is 1, your currency, local currency, doesn't depreciate. You see why we are always trying to be mischievous. And I'm coming to data wrangling to let you understand why data wrangling is very important. Because if we want to know the actual if you want to know whether the balance of trade in Ghana here is actually 1 or not, check the how the cedi is performing. If the balance of trade is 1, there is no way the currency will depreciate. It will never happen. But why is it that our balance of trade is 1 and then the currency is still depreciating? Data wrangling. Because we have refused to reshape the data that we have used in calculating. We are actually exporting the same as we are importing. But what we are exporting, a lot of the export does not belong to Ghanaians. So it doesn't bring back hard currency into the country. Talo is exporting, ExxonMobil is exporting, AngloGold Ashanti is exporting. All of them put together form part of the export volume. But how much of the export volume belongs to Ghana? That's the problem. So what is it? All these guys I have mentioned, they are the giants who are exporting, and they don't bring the money back here. They export it and then they keep the money in the foreign banks. So you may think that, okay, our export trade or our balance of trade is 1, but you see that your currency will continue to depreciate. Now you find out why are they getting it wrong? Data wrangling. So it means that for them to calculate the actual balance of trade, they need to take out that outlier. They need to take out ExxonMobil. They need to take out AngloGold Ashanti. Take out all those foreign people who are here and then they are exporting and they don't bring the money back, and leave only exactly what we Ghanaians export, and that brings back hard currency into the country. When we do that and we calculate our balance of trade again, you see that we're going to have what? Realistic value. So this doesn't happen only in that place, it happens everywhere. So data wrangling simply means that take care of those kind of data variables or data points that are likely to interfere. The second thing is data arrangement. In data wrangling, okay, I will even come to data wrangling, the step-by-step for data wrangling. So, but that's what I want you to understand. Data wrangling is about reshaping the data, taking out outliers, realigning the data, and then knowing which particular data point you are supposed to relate to another data point to have your output. So that's the second step in machine learning. The third step is choosing a model. We have given much of the models up there. It can be a logistic model, it can be a linear model, it can be random forest, it can be a vector machine. There are quite a number of them. You can choose any of the model you want. Now, after you have chosen your model, you should know why you are choosing that model. You should know why you are choosing this model. If you are dealing with data that doesn't have direct relationship, don't choose a linear model. For instance, I've already given some example that if you are looking at the relationship between two variables, they are always having direct relationship. But if the variables on one side are more than the variables on the other side, don't choose linear model. If the predictors are more than 1, it cannot be linear. So it should be something like logistic model. You see, and then just know that. Now, after you have chosen your model, then you now train. You have to train the model, and this is where we now take the data set and partition it into training data and then testing data. Then we use the training data to train the model, and then we use the testing data to try it on the model and see whether the model will get the same results as how. So the training data is like you are telling the machine that take this data and study it and give me outcome. So the machine has studied it and has given you an outcome. Say, okay, all students who are wearing boxers to the buttock level are likely to be thieves. Sorry about that. So you now take the third one and come and give to find out whether, and then with the testing data and find out whether to be able to predict those who are thieves there or not. And then that's what happened. Now you come to model evaluation. The model evaluation is what I just explained momentarily. You are much more going to find out whether the model that you have done is it a good model or not, or does it actually do the work. So that's where you go and pick a foreign data or data that is unrelated, that is not part of the work that you were doing. That's not part of the data you are using. Foreign data, and come and try it on the machine and see whether it will work perfectly. Then you are evaluating the model to find out whether the model is performing well or not. Yes, please.
So at the stage of training the model, if you have unsupervised data, how are you going to be able to do that?
What is it? If you are looking at unsupervised learning,
yes, please. Yes.
It's the same approach. It's the same approach. You just partition the data into two, and then you use part of it and allow the machine to to go through the same process. So the machine will just take the 70%, go there and find out whether it can do the clustering, and when it finishes, then you take the other 30 and try it and see whether it will be able to do the same clustering. So when it is done, then you evaluate it, and then evaluating the model, there are several ways to be able to do that, and then it can tell you the performance of the model, whether the model is able to. If it is, we have already done it, but maybe you haven't paid attention to know that that's what it is. But actually, when we see the R squared value, which can give you, let's say, this, you can always say that the model is doing well. But sometimes you may want to try your data on different models. After that, you compare the models to see which one did better. And then we will come to plenty models, and then we can try all of them. And then I will also show you how to be able to compare the models and evaluate their performances. And at the end, we can see that, okay, this model does much more the other one. Then you choose that one as your model. Then your program is now written. So that's it. It's the same approach. Whether in supervised or unsupervised, is going to be the same approach. Now, the parameter tuning. What is it? At this particular point, what are the parameters, the data points and whatsoever that you have? Some of them, you may have to, you may have to work on them. If not, it's going to affect you. You are looking at household income and how it affects somebody's ability to secure a loan or not. And then you have the entire village, all of them are farmers. Then you go and bring somebody who is a lawyer there. And the lawyer is collecting how much a month? He's taking like 10,000 Ghana cedis a month. That's, you need to retune those parameters. If not, you are going to think that, the model is working well. It's not working well. I think there are things you need to retune them. And that's where the data normalization comes in. You normalize the data. We will look at how to do that. And then the last one is prediction. Making the prediction, that one is simply to just pick some two variables and put it there. Okay, after I have done the model and I'm there, I'm saying that, okay, if you see this bacteria with these features is a pathogen. If you see this bacteria with these features, there's no pathogen. Then you go and pick a bacteria with some features and come and put it there. The model will predict that it's a pathogen or it is non-pathogenic. Okay, and that's it. So these are the steps that one need to follow to perform data wrangling. The data wrangling, because when we go to the studio, much of the work is going to be data wrangling. I'm telling you, data wrangling. That's what we need to get. When you get that right, the rest is just simple. First of all, data discovery. So in that case, that's when you are supposed to get very familiar with your data. And all the data scientists will tell you that don't play with this part. If you don't understand your data, it's a waste of time. You will do everything you can interpret, and it's very common. It's very, very common. Yesterday, I interpreted some data on Facebook about what is it? Life expectancy across the globe. And then somebody sent me a message. What is it? I realized that data interpretation or understanding your data is very important. I think the guy might have done the similar work, but he didn't understand the data, and interpreting it became very tough. So to be able to interpret your data is to understand, to get so familiar with the data, get much familiar. And how do you do that? Check the structure, check this and this, do some little exploration, find the mean, the median, find the 5-point summary. Is going to give you a clearer understanding of how the data is misbehaving. Check for missing values, whether you are replacing, you are not replacing. Check for the structure of the data, the arrangement. So which variable come before the other variable and whatsoever. Which ones are dependent, which ones are independent, which ones are predictors, which ones are response variables. Discover the data very well. The second thing is data structuring. The data structuring, every single model that you are going to work with, it takes data in a particular format. I've spoken about this before. Some models are there, the data will have to be in matrix form. So if you don't transform the data into a matrix, the model will not be able to work. Some work on time series data, so it's not a data frame. For instance, if it is a rainfall pattern you are dealing with, so it has to be a time series. If it is a forecast data, let's say you want to know what will be the population of Ghana in 2035. So you want to know the GDP of Ghana in 2030. You want to know the disease burden of people in Ghana here by the year 20. That is time series. So the data will have to be in what? Time series data. Time series, we use the function TS. So if the data was in data frame, you have to restructure it into a time series, given the duration that you want it to be, and then you can now begin to do your model based on that. Okay, that's the structure. If it is a correlational work, you want to know how much the variables are correlating. You have to put the data in a matrix form. If not, it won't work. You see, you have to also put some in a tabular form. For instance, that data I was talking about yesterday, I have to take it into a tabular form. It has to be in the form of a table. Some will have to be in the form of a data frame, and then in that order. Some have to be in an array. So that's the data structuring. And then data cleaning. This one, I think that we are much more comfortable with it. That's you are tackling outliers. I've spoken about outliers. What is it? You are there. But recently, my boss was telling me that he's doing a paper on outliers. Most data scientists will tell you that take the outliers out. But outliers also, you guys, let me hear your opinion on this. Do you think it's always good to take outliers out?
I don't think it's always good.
Why?
Because in living things, we have some people that always be the extreme. So if we think that this particular extreme, it could have been as a result of a mistake, it prevents us from going deep into understanding why this extreme okay. In life, let's say an example I would like to give is some people are probably immune to some ailments or diseases. So in the case of a severe outbreak, and almost everyone is showing signs and a particular person is not showing, you refuse to take whatever vitals from the person. In future, it will not help you understand why this particular person was resistant to the outbreak.
Okay. All right. Eben.
So I agree with we having the two sides. I'm agreeing to the two sides of the whole point, but if it is too extreme,
yeah,
then it's okay to get it out.
Okay.
So that we could have a model that can be standardized.
Okay.
But
what do you think? What should happen to the outliers? I'm looking at children. I'm checking for my Norris kids, and every child is weighing 2 kilograms. At a point, one of them is weighing 50 grams. Should I add to my analysis, or what should I do?
So I was thinking, if possible, if those two outliers can also be analyzed, so that something can be done about the two outliers.
Okay.
That will make it a holistic approach Yeah, to
Okay.
your analysis.
All right. Then what is it? The two of you have clear understanding of outliers. There's no point making. But have you noticed that here I was saying that maybe the outliers like making corrections and then deleting bad data. What is the difference between? I mean, what do you consider as bad data? Bad data. Is it the same as outliers? Let me get your opinion on this.
No. Bad data,
Okay.
to me is not same as outlier.
Okay.
Let me say if we are measuring the height of adult,
Yeah.
and we know that even let's say the height of adults in Ghana, and we know
Yeah.
that in Ghana, we know that the whole world, the height, the maximum height you can get is 15 meters. But you measure someone in Ghana and the person is giving you 4 or 3 meters as the height of that person. It should tell you that maybe the person wanted to type 2 and mistakenly pressed 3, which
Yeah.
is bad data. That's
Yeah.
how I understand.
Yeah. What is it? Bad data is mostly data that is contaminated. You see, and is much more in genomic data. Bad data can also be it can also be something like transposition. For instance, you are dealing with male, but at a point you see female there. Okay, so you need to take that out. You are dealing with adults. Your data set is supposed to be adult, 18 years and above. At a point you see somebody with 15 years. Those ones are not outliers. So the difference between outliers and bad data is that outliers what it is within the scope of the data, but it's just extremely far away from you need to take that person out. I am dealing with children under 5, and then before you realize you see somebody there 18 years. That's a bad data. So for bad data, there's nothing you do about it. You take it out. We are dealing with when you come to genomics, and when you have done your quality checks, then if you bring out your multi QC, and then you see I have multi QCs here. Because most of us are not in, maybe we may not be in genomics, I would have displayed for you to see. You see that some of the reads are not correct. They are completely bad reads. You just have to take them out.
On
Come again?
Data. No, I said I'll be doing something on genomic data.
So I said I'll be doing something on genomic data.
Yeah, just
wow. What I didn't know that.
Maybe 6 years, 2 years, right?
Okay. So I'm just trying to see. All right. This is a FASTQ file. Where am I? Okay. So, okay, this is trimmed. Okay, some of them are not trimmed. I'm trying to open it, it's not opening. Maybe I've deleted the file that is. Okay, if you are watching, you could see this is the FASTQ. What is it? These ones are the trimmed ones. I wanted to open the raw one for you to see how what it was, so that we could see the FASTQ files, and then the bad reads, to be able to identify the bad reads, and we can actually trim them off, or we can just remove them completely. That's a bad data. There's nothing you can. The ones that are not bad all that enough, we just simply make sure that we we trim them off. We trim only the bad aspect, and then not entire read. We just cut part of it out. But I'm not getting it as quickly. Okay, I was having read alignment here, variant calling here. The read alignment. I'm not sure I have. All right, are you there? Can you see my screen?
Yeah.
So you can see that. Eben, are you familiar with genomic data analysis?
No, please.
Then.
No, please.
All right, then. I'm sorry, but what you are seeing here, each of these are they are reads. A read is like okay. I'm not going to bother you about that. I just want to illustrate. But all what you are seeing here are read positions, and then you can see that anything that has entered the red here, that thing is bad. That particular read is bad. So from here, where my cursor is almost down, those reads are bad. We need to cut them off. So, and then those that are in yellow is warning. It means they are not too good, but they are not also too bad. So we need to also trim them off. And so when we trim, we are able to have a very good outcome. And then look at the graph here, telling us where we have the bad ones and then the good ones. So we can see what is it. Today I'm not on genomics. I'm going to be teaching you what is it, GWAS very soon. So this will be part of the things I'll be doing. So, but these are, what is it? You can see the DNA, you can see the output and whatsoever. Now let me get back to, I was just trying to illustrate the bad data and then how to take it out. So that's the difference between bad data and then outliers. Sometimes you also need to make corrections. What is it? There is nobody, if you are looking for people ages in data cleaning, you are looking for people and their ages before like somebody is, what is it? Let me ask this question and see what I...
Okay, hey, sorry, 1,020.
1,000 and then 20. Okay, 1,020. All right, so you are dealing with kids, children, and at a point you see somebody's age, 120. Polly, you have a child. I mean, what will come to your mind? You are analyzing
this person
children.
Wanted to type
this person wanted to type 12.
12. The person wanted to type 12. In fact, somewhere in my data science class, somebody actually taught me how to be able to identify. Somebody can type a word. If it is a text, if you are watching my screen, I'm going to type a text and make a mistake, and then you tell me what I was trying to type there. So
we can see you typing. Okay.
We can see you typing. Okay.
Can you see this?
Yes.
So I was going to type a particular word. What word is that? All right, now wait, let me change it this way. People. So, I mean, without you even knowing at all, have you seen this I? The PI here. The I there, the I is closer to what? If you check on your keyboard, I is closer to which? Is closer to what?
To O and U.
U and
I.
O.
U and O.
Exactly. So it's most likely that's how you are able to determine what the person was likely to do. It means I was going to type U here, and I didn't see it before I realized I typed this. So in data science, you always use those intuitions to be able to come out with. You are dealing with children. Somebody write 150. The person wants to write 15. You see, sometimes you see 105. The person wanted to write 10, mistakenly added 5. Sometimes, even though some people will say that it's not right. Now, data enriching. That's the other step in data wrangling, data enriching. You are combining your raw data with additional data form, right? This point, data enriching is like after you have had your data sets and the data set is there, you have done all sort of corrections and whatsoever, the data set is now ready. Now, this is the format in which I want the data set. You can now add other data sets to it. Because you have already set out the format. Okay, I want the first column to be age, second column to be height, third column to be the allele number, the third one to be, let's say, whatsoever. Now, when I have done that, I can now begin to add any other data set from anywhere that I am. So that's what we call data enriching. After you have reshaped your data the way you want, you can now add any other data. So all those, if I want to add people and their ages, I can add, because I've already set out that, okay, I want age to be the first column. So I'll now be adding it in that way. And then we have data validating. What validating is just to cross-check your columns and then to find out whether the data entries are in order or they are not. You are just validating to find out. And one of the easiest way to do this is to find the mean. You can, if it is a numeric or integers or double or whatsoever, you can just try to find the mean. If it is factors, find the levels. Immediately you put levels and the levels are not coming, it means there's something. So you do that to find out whether the columns are valid or not. The publishing the other one is like, when you write any paper, definitely the data will have to be published. Some people also just publish the ordinary data. Data scientists don't think that the other people must analyze data. They always think that yours is to get the data and publish it. And that's why when you go to Kaggle, there are over 2 million data sets. The data set we are going to use, I picked it from Kaggle. And so now, that's the various ways through which you perform data wrangling in machine learning. Very, very, very important. That's all about machine learning. It's about data wrangling. When you get it right, the last part is just zero. It's just zero. It's just two functions, and then that's all. It will bring out whatever you want. Now, the most often used data wrangling functions. I mean, what I have said here, you have to get familiar with this data restructuring, with taking outliers and whatsoever. How are you going to do that? These are the 5 or 6 most important functions that you use in data wrangling. Select. This function, select. So you select from somewhere and do something with it. Then rename. You can rename your columns to suit whatever that you are doing. You can rename the entire data set. You can rename the variables. You can rename the factors. Okay? Then arrange. Like, you sort the data in order of how you want. That's what I was saying. You have to maybe sort ascending, sort descending. Or you can unsort. Or you can rearrange the columns in order of how you want it to be. They are all part of data wrangling. You use the arrange function to be able to do that. Filter. There are some things like we're talking about the outliers or those that are bad data, you want to take it out. You filter it out. Filtering. It's also done in genomic data. If you know, you filter some of your reads out or you trim them off. So the other function is mutate. The mutate is like you could generate actually new rules. Like, for instance, you want to replace something with another thing. You can actually use the mutate function. You want to replace female and male with 1 and 2, or 0 and 1, and then in that order. You can replace colors. You can replace religion. You see, sometimes in data science, there are some things you always want to hide. If you don't do that and you publish the data, you may have problems. For instance, if it is about religion and you analyze the acceptance of all the religions in Africa, then you go there and then you keep on mentioning a particular religion and the acceptance is low. Trust me, you don't know the one who's going to review the paper. He will mind you. People are so emotionally attached to religion. So what you normally would do is you use these dominant variables to just represent them. And then, so that's another thing I forgot to have added. in data wrangling, like dummy variables. So here, after you have mutated, you can give dummy variables to all, to those things like, okay, Christianity is this means this, and that's all. So later on, so you replace them. That's the mutate function. So basically, this is what I want us to have a clear understanding of what machine learning is all about. Before any questions so far?
I want to question
Go ahead.
Most of them,
Your voice is very, very low. Okay, I can't hear you. Yeah.
Most of them we are fond of using mean.
Mean.
Yeah.
Okay.
Data, I don't know. But there was a time I had a data where the points were wide apart. He said I shouldn't use arithmetic mean. He mentioned
Is it harmonic mean?
Harmonic mean.
Yeah.
How is that one different from the why couldn't have then use median to check how the data is spread than he asking me to use a harmonic mean.
Great. So I'll answer the question this way. I'll tell you why there are instances you are not supposed to use mean. We've already answered it here. Your data is not sequential, or not sequential. It's not uniform. There is so much diversity within the data set. So it means that the difference between one value and the other is just too wide, or the difference between the lowest and the highest is extremely too wide. So when you use mean, it's going to be telling lies. If you have all the student stipend is around 1,500 Ghana cedis, all of them 1,500, but you also have some students who are taking 300 as stipend, and others are taking like 10,000 as stipend. Those two values is going to affect the mean. So when you are going to come out with a stipend, the average stipend in KNUST at 2,000, let's say 2,500. And so you are going to communicate that and say that the average stipend received by a student in KNUST is 2,500, which is not true. So the best way is to go for a mean that harmonizes, that take care of those outliers. So if you check the formula for the harmonic mean, you see some form of normalization there. You see some exponential something there. Mostly in data science, when you see exponential something or kind of logistics, is much more of like normalizing the data. It always normalize the data means that to take the excess and allow the data to be at a different pegging or at a level pegging, so that you can then find the averages. So the harmonic mean will take care of those excesses and be able to give you a correct representation. The other reason could have been that maybe your data was not continuous. Mostly, it's not good to find the mean of a categorical data that is based on, let's say, what is the number of females. You want to find the mean. No, you can't find the mean of the females or the mean number of students in KNUST here, you want to find the mean. What is
The
it?
data actually,
You mean is not good for categorical data. All right. So if the data was categorical, mostly median is always better, or the mode. All right. Each of them have their good side and then their bad side. If you are dealing with continuous data, then mean is always the best. But if you are dealing with categorical data, it's not continuous, then mean becomes a little bit of a problem. It becomes problematic. So these are the two things I think maybe your supervisor suspected. That maybe the data was much more categorical. Maybe you were dealing with count data, jumps data, dealing with number of bags. And so you are not dealing with, so if you, or you are dealing with, if it is animals, number of bears per hectare, number of cattle, number of this. So when you do that and you are looking for mean, I mean, we don't have animal. So the mean can give you 2.5. Who is the 0.5 animal there? You see? So the median is always the best. But if it wasn't these two categories, but it was a continuous data, even though he said you should use the harmonic mean, I suspect that the data was not all that normalized, or it was not all that, the diversity within the data was much high. And then the standard deviation was. Mostly, you refuse to use mean when you have tested your standard deviation and it's extremely high. If I'm looking for the height of all the students in KNUST and I have a mean height of 1.6 meters, and then the standard deviation is almost 3 meters. It tells me that there are some people in KNUST who are almost 6 meters high.
Yeah.
You see? So standard deviation always tell you how the data departs from the mean, from the average. And so when you see the standard deviation extremely too high like that, Charlie, just make sure that you go for something else. You go for your harmonic mean or something like that. Yeah. I don't know if I've made sense.
Big Bright, in our studio, how do we represent harmonic mean?
Okay. When we go to our studio, I will try that.
Okay.
So, any more question from here? Paulina, have I answered your question?
Yeah, yes, please.
Yeah,
I
yes,
haven't
please.
gone
I haven't gone
in my
I
I
thought you had gone to sleep.
Gina,
Come again.
Gina,
I said the data was on.
I said the data was on
Gene expression.
Yeah,
Okay.
Yeah,
So,
But-
you see,
but
some of the
some
samples,
of the
I don't know
I don't know
the
whether
screen
the
house,
screen house
had
had
the
So-
light there
the
was-
light there was
okay. So, if it were on gene expression, actually, you were looking at, I don't know, but I suspect that you were actually trying to find out the genes which have maybe higher expression, or what the genes which have been expressed, or the average genes which have been had this kind of in any case, the genes they account what's the data. If you are dealing with individual genes, the genes are always, you don't have half gene. So I haven't done RNA-seq. I did comparative genomics, but I have fair knowledge about RNA-seq. So I'm thinking that if it is gene expression and you are dealing with individual genes, so genes, you don't have half gene. So if you are looking for the mean of if it was about the genes and you are looking for the mean, what I'm thinking that because the gene expression, each of the gene is going to have their expression level.
Yeah,
Each of the
the
sample.
Yeah.
You know, I have
rep one, rep.
Yeah.
So the
same
treatment across the board of species.
Yeah.
Somewhere it's higher level.
Okay.
So I needed to combine to get the average expression.
Yeah. So I'm suspecting that it was that reason. It was the reason of the fact that genes are always count. They are count data. irrespective of how many they are count data, and we don't have even how many genes can we have? Human has 23,000 genes. No, it's not much. So in that case, if you were looking for the mean expression, it were going to count the number of genes. And if you had given you 20.2, so you are saying that there are 22.2 genes which have this average expression. That's going to be a problem. Scientists, they like criticism a lot. So they will ask you, who is the half one? Who is the 0.2 gene? You see? Scientists are the most two known you can ever find. They're always looking for problems. They don't actually pay attention. When you present your entire work, they are looking for faults. That's all that they do. They don't have time for the good ones. That one, they just leave it like that. The faults. And so my boss will tell you that when you're writing a scientific thing or when you're doing a scientific analysis, as much as possible, avoid where they will tackle you. Okay. All right. So we don't have much time, but let's go to RStudio and then check some of the things that we have mentioned here. So we are in RStudio now. So I'm going to copy this link. Yeah. Can you see my RStudio?
Yes, please.
Yes, please.
Okay. Okay, let me check mean and check whether I have an alternative way of checking for mean, harmonic mean. I think one of you should check it online for me, or I could check it online. I could check harmonic mean in R. I think it's all part of the learning. Harmonic mean in R.
It's harmonic mean.
Yeah. Okay. It's actually a time series package in time series. What is it? I don't know but my data is good. Today my internet is flowing well in the house. So I have this a matrix, this. Okay. Now I've seen it. It actually uses the actual name harmonic. It uses the actual name harmonic to be, but you need to identify what is it? An index. You have to give an index. Until today, I just know harmonic mean in statistics, but I've never used it in R to do anything. So I haven't come across the function.
Robert, can you type harmonic in the search button, please?
Search button in R.
No. Where you were? Google.
Okay. So that's where I am. So harmonic mean.
Initially you type harmonic R.
Okay. Okay. You are right. Harmonic mean in R. Thank you. Okay. So now what is it? They are here. It's actually come with a package. It's not these days. Everybody wants you to be part of their program. So let's say I have this vector here. So I can actually print the harmonic mean of that vector. So it actually uses the harmonic.mean. That's the function. It uses harmonic.mean. I don't know why it's not coming.
You need to
install.
I need to do what?
Install
You
the
need to install
package.
the package.
The package.
Which package does it come with? Let me see. Yeah, there's a package called Psyche.
ESYCH.
Harmonic.min data. But this is available inside. Yeah, there's a package called Psyche. Psych. How do you pronounce this word? Is this psych or psych?
Side.
Yeah, okay. What is it? I'm not in England, so what is it? What is it?
The Queen will tell us. That's
those
it.
of you who are,
That's it.
what is it? Those of you in England.
Yeah.
Knapsack sprayer, then they'll say
Yeah.
knapsack sprayer, then they'll say knapsack sprayer.
Come again.
Knapsack sprayer.
Ah,
Knapsack
okay. It is installing. And you see, all right. Thank God, my data is. You guys today. I think that we are just lucky. I wanted to go and do this tutorial in the office because I wanted to also do my biometric registration. I got to the office. My boss was there. If my boss is there, he won't allow you to be making noise. He will tell you to leave. So what can I do? So I came back. I only got back to the house here. Lights had gone out. So I was just sitting down. When it was almost time, then the lights came, and I said, So now it's there. So I'm going to library Psyche. How was this spelled? S.
ESYCH.
It has come. Yeah, it has. So now let's say we have harmonic. Now it comes. Harmonic mean if I were having a vector. Okay, so I can even, because I have some data here already. So the train, this is the data set that we are going to work with now. So I could just pick one of the columns there. There's a column on age. So let me find out the harmonic mean of the ages there. So it says it's about 14.79. That's the harmonic mean of age in the Titanic. So let me find out the harmonic mean well. So I'm going to say
That's
harmonic.
all me.
That's all me. Oh.
No, I want to find out what what does it do? So we just put a question mark by it.
Okay,
And so
I wanted to see the difference between
okay.
the
So we
harmonic
could
and the
actually
harmonic.
That's all me.
okay, then let me just copy this. I'm just going to enter here, put that there, and remove the and leave only the mean. Run that and see. See that the actual mean is 29.5. The harmonic mean is 14. Can you sense something there?
Interesting. Yeah.
Interesting. Yeah.
Yeah. Perhaps if I check the standard deviation. All right. So let me copy this. Turn it down here and put it there, and then check for the standard deviation. Do you remember the standard? How to find standard deviation of something?
Yeah, just
Yeah.
So the standard deviation is actually 13.4. Now, can you see something there? The mean is 29, standard deviation is 13. That's way too much. So it means that there were people there who were very old and there were people there who were very young. Can you see that?
yeah.
So it means in the Titanic, we were having people who were as now let me ask you this. You put this question. I mean you brought yourself. This is the original mean 29 years, 29.5 years. But the standard deviation is 13. What is it? 13 years. Now just looking at these two figures, when you pick somebody from the Titanic, that's actually happened. What do you think the person is likely to be or what is likely to be the youngest person there? What would be the age of the youngest person?
16.
16.
Eh?
16 years.
16 years.
No. Check. This is the mean age. But there's a deviation of 13. There's a deviation from the mean by 13 years. 13.4 years. So, what is likely to be the youngest person over there? Did you say how? You say what?
16.
What did you say?
16.
Yeah, 16. Yeah. You are right. You just deduct from this. Deduct 13 from 29, and then you have the youngest person there. So, what the person was likely, not actually 16, but the person was likely to be around 16 years. So you can see that this one, if you were running with this, you will say that, oh, okay, on the Titanic, almost everybody there was around 29 years. That's what average tells us. But in actual sense, there were people there who were actually 14 years old. And the standard deviation confirms that. So that's why the harmonic mean is always very relevant, especially when you have a data set with a lot of diversity. It's not quite uniform. Paulina, I think this is now much clearer, or?
Yeah.
Yeah, thank you. So now, I don't know how to get this data across to you guys. Let me try and see what if I can attach it to your WhatsApp. So let me check on Eben. Eben, I'm trying to see if I can attach it to your document. I actually downloaded it and I named it. It's on my desktop, Titanic in capital letters. I don't know how huge it is. Okay, it's here. You can see that it's a lot of. So I'm attaching it to you to see if it goes. Then forward it to Paulina.
Paulina.
Okay, yeah, it is. So now, by now, if the two of you if you take the data, don't just keep it somewhere. I'm going to show you what you'll be doing, because right after this, I am copying the whole of this course and I'm sending it to you. So you will repeat exactly what I have done here. Initially, I picked this particular code to. This is the online site where the data is gotten from. So you can see the data says Titanic.csv, but I later on noticed that this particular site didn't have the entire data set. So I went to Kaggle and downloaded the data myself, and then that's what I have sent to you. So if you use this particular link I have here, if I send it to you, you can follow this tutorial, because some of the variables are not there in this particular link. And that's one thing you should be careful when you are studying things online. Some of us, we have not gotten to know some of these things. If I'm following any tutorial online, there are a lot of things I see that they have intentionally omitted. If you follow this particular tutorial, you can see this tutorial everywhere. It is online. But the online version, when you take it with the course here, it won't work. If you think I'm lying, I can copy this link and send it to you. And then you try it and see. It won't work. There are some things the person has intentionally, opted out. So I took that out. So you see that when I send you the links, the course, I said from here going. So what you need to do, what you have now, if you download the data into your computer, by now you all know how to import the data. It's actually a CSV file. It's a text file. So you go to your environment pan, and then you come to from text. It's a text file. So you are going to import it from text. It's not CSV where you use base. So you click from text, then you come and browse. So obviously it's going to be on your downloads. You go to your downloads. I kept mine on desktop because I have changed my working directory. I was doing some tutorial yesterday about that. So I'm going to check on my desktop, and it is here. If I click on that, then if I come, the data set is now loading. Hi. All right. So when it loads, any other thing here, please don't touch anything. Just leave it the way it is. It's a text file. Don't trim any space. The spaces have been trimmed already. So if your trim spaces are not checked, please check them up. And then in that order, after that you import. I've already imported, so I won't import it again. Now when you import it, you see that I assign the name Titanic to this called train. So if I do that, run it, you can see that I have it here. I can just have a glimpse of it head. If I pull this up, so now I don't need this part of my arrow. So by now you should know some of these features. So when if you do your data, you should do the first thing that we were talking about. We're saying that in data science, the first thing you have to do is data collection. And the data collection, I said, that is where you need to verify a lot of things. And this is what we are going to be doing. I'm sending you the 2 documents. So don't follow typing for now. Just watch so that we don't even have time today. So first of all, you check the heading. The heading will tell you that, okay, the first column is passenger ID. Then the second is survivor.
Sorry. When we imported it, was it CSV file?
No, text file.
How did it come?
Text file. It's a text file.
Text file. Okay.
Yeah.
Okay.
So import it as a text file. All right. So you will do the heading and check all this. Okay, this is how the data is being partitioned. First is passenger ID. Survive, follow. What is it? The class. You know, if you have been to a cruise ship, you know that there are classes. First class is there. I live in here. There's a premium class. It's only Paulina who has enjoyed that. I've never seen that. The name, followed by names, followed by sex, followed by age, followed by what is it? The siblings. How many siblings were there? Then this patch, I don't really know what it is, but to know what this is, put a question mark by the data set. Arrow will tell you everything about what each of them is. Another thing is do glimpse. All right. So after that, you can come and then what is it and check the structure of the data. So you have structure, train. All this come under data collection. No, I put strain. If I run that, so you can see that it has given us all that we are looking for. Some of them are numbers, others are characters. I think it's just numbers and characters. So it also tells us the information that we are likely to change some of them into factors. Now let's look at dimensions. These are the few things I was saying that we should always do under data collection. So there are about 891 rows and 12 columns. And then in which class it is. So we check that and we would realize that it's actually a data frame in a table form. There's a difference between data frame and data frame in a table form. Data frame in a table form, the data frame has been described. Data frame without table, the data frame is not described. All right. Now we could cut glimpse. Glimpse. Okay, glimpse is not coming. In R, you need to know the packages that come with some of the functions. This particular package, glimpse, works under what a tidyverse. So if I come here, I'll have to just search for my tidyverse and then come and activate it. Now when I do that, before I finish typing glimpse, it should come. Yeah, now the glimpse come. Then if I put glimpse and then I put it there, train, then that should be able to give me much more clearer information about the data, but some of them are double. I told you that in data science, when you say if you hear double, it means it's a decimal. There are decimals in it. If we're doing Python, you would have been tired of hearing double by now. So the other thing we need to check is to come again.
The double.
Okay. If you say glimpse, the glimpse will tell you the number of rows, number of columns. The second thing is the columns. So the passenger, you can see it is what? Double. DBL. DBL.
So what does that mean?
It means that data could be 1 point something, it could be 1.
Okay.
So mostly those who do coding, they don't like using integers. They use double. Because when you use integer, if you use double can accept both integers and non-integers. But when you use integer, it cannot accept the double. So to be on the safer side, use the one that can accept the two. So when it is double, even though you see all of them as integers, but it has been coded as double, no problem. So later on, if it is 1, no problem. If it is 1.1, no problem. Okay. So you see that there are double and characters. Okay. So we've checked that. The next thing we need to check is to find out summary. And then, the summary is going to tell us whether some of them there are missing data or there are no missing data. So the summary of what train. So we're going to do that. And then, so we can see that the characters is going to leave that out. It's only going to count them, the characters. It will only give you the. So, but those that are numerical, you can see that all of them came. So there are no missing values. But you know that the best way to answer the question of whether there are missing values or not is you say is NA, is NA and put into bracket the data train. You see that when if I'm getting tired, I'm always typing wrong things. So when you do that, it's going to return a boolean, and you can see that there are some, wherever you see true, it means there is what? A missing, there's a missing data there. Can you see true there?
Yes, just a few.
Yeah. So it means that on our way, we have to find a way to clean this, and that will come under data wrangling. All right. So now we have checked some of the things about the data collection, and we've noted that, okay, this is how our data is working. So the next thing is, okay, if I know there is something about, I need to reshape the data. And the next point is what? Data wrangling, the one we just spoke about. So we need to wrangle the data. We need to reshape the data. And so one of the easiest way to reshape the data is to replace missing and then we are just going to replace them with, or we are going to do some few things there. First of all, we need to come out with a table in the form of a table, and then to be able to locate. And we are going to form a table of those who embarked, because that's the primary focus of all of them. The people who embarked on the trip. The people who embarked on the trip is our main focus. So we are going to form a table of those who embarked on the trip. So use the function table, and then if I'm going to run that, so you can see that we have those who embarked on the trip. We have those who were in these categories C, Q, and then S. This is why I should have done the question mark to be able to understand the embarked, what all of them means. And I think I need to add that to my data collection features. For instance, I should have done question mark and put train, the train, run that. All right. So when you do that, Oh, what is this? There's no information on that. Because it is not an inbuilt data in R. That is why I am finding it difficult to get it. The train is not inbuilt data in R. So if I do question mark, R doesn't generate any information on that. But I could actually check on online to find out what that means. Because the Titanic data set is a popular data set. Everybody knows what it is. But I'm thinking that this might be of different classes, of maybe those who survive, those who... I'm thinking of the best way to know what that means. Those who embarked, they were of different. So we have the C.
Go to the data. Can we go to the data itself?
The data itself. The data itself is here.
Yeah. So that we go to the column and back.
Okay. So see how the embarked are. They are. We have S there, but I don't know what the embarked means. I know that the embarked are those who embark. What is it? Who? Okay. Now I've gotten it. Different people embarked at different. Should we call them harbor? What is it? Harbor, or where the ship pick people. They are different harbors. So some embarked on this particular harbor. They abbreviated it as S at Q and then at C. Yeah, that's where the embarkation took place. That's where they were embarked. Thank you. Where was I? I was here. All right. So we try to use that as a yardstick to be able to check for our data wrangling. So we form a table of that, and we can see the table is here. All right. So it's just 2 rows, 3 columns. Then for here, we are now going to say that under that particular data of embarked, we are going to go there. Remember, the whole of this is like the embarked is a vector. And in a vector, when you put a column like this, you are actually trying to locate some, you are trying to subset a vector. We don't have time for me to illustrate a lot of things. Can you remember this? Don't always look at the code to be too long. This code is like you are going to subset a vector, and the vector name is embarked. But in this case, you are not just going to subset it. You are going to look for not available. Anything that is the same as not available. Remember, in R, when you say double equal sign, it means you are saying that what is equal to this. So it's going to check through the embarked across the entire table, and anything that it found to be not available, NA, it should replace it with S. And the S is actually one of the boarding places. One of the places that was boarded. So we're going to run that, and then is now, what is it? It will replace them. That's one of the ways of doing taking away the missing values. Okay, so we add a feature for tracking the missing ages. So we come here. I'm just going to look at the summary of. So you can see that we also have something like NAs, and the NAs are 177. That's not available. The people whose ages were not given, they are 177. So what do? We're going to say that, okay, the train under the missing age, it means that we are creating a new column. Okay? We are creating a new vector in the columns of this particular data frame called train. And that new column name is missing age. And we are saying that if it is NA, if you find NA within the train data under the column age, replace it with yes. If you don't find it, replace it with what? No. This is what the code is all about. Right? So we run that, and we can have our yes and no. So now we come to add a feature for family size. This one is what it is nothing. So you go to the family size column, and then we are just adding 1 plus the siblings, and then to the patch. What was the patch all about? The patch. There's something. The patch. What was the patch all about? I needed to have had a complete description of the data. It's one thing I didn't do well. Should have checked for that. Okay, I'll try and add, and I'll try and get that before I send you the course. Okay, so we just run that, but this is where this particular part, what we have done here is simply where we are dealing with the data wrangling, but we haven't finished. Now, the most important place in machine learning deal much more with factors, because it's dealing with present, absent. It's supervised learning. So we have to change most of the data set there into factors. For instance, those who survive. 0 means you didn't survive. 1 means you survived. So what do? We change that particular column into factors. So we just say as factors, then we go and look for that. So when we run that, all of them, we are changing the whole of those variables. Survive, the class you were, first class, second class, sex, whether you were a male or female, embarked, whether you were embarked or you did not embark. Shit, what happened?
What?
Whether you embarked. Yes, something happened. My computer just went off. It has come. Can you all see?
Yeah.
So at this point, you've noticed that you are actually looking for survivor, you are looking for the class, you are looking for sex, you are looking for embarked, you are looking for the missing age. Remember, the missing age, we have already replaced them with yes and no, and that also has become a variable. Okay, all right, so we just ran the whole of that. We are changing all of them into factors to make sure that they now have levels. When we have done that, now we are now coming to look for something we call we are going to select the columns we are going to be working with. So to subset, it's like subsetting a data set. This one, there's nothing in it. You just look for we already know that survive is a column, P class is a column, sex, age, and whatsoever. All of them are columns. So we pack all the column names just like the way they are spelled into a vector and give it a variable. This is the variable. So when we run that line, it runs properly. So we now come here and say that under the train, we want to select all those columns and then leave the other columns, because the columns are many. And how many are we selecting? We are selecting about just 1, 2, 4, 6, 8. We are just selecting only 10 out of the rest. We don't need the rest. And this is the easiest way to subset. In fact, if it were me, I would have used a square bracket and say 1 is 2. But they are not following each other. I should have asked you this question. The columns are not sequential, so you have to use a vector to be able to select that. So instead of typing inside the C here, you can put it as a variable and now come here and select the variable. So now our new data set is now made of only these columns, leaving the other columns out. So here we can, if you check for the structure, you don't need to do that. Now, the most important stage in data or in machine learning is impute. The imputation is a function written in R that allows you to work on your missing data. So all the missing data we have in 177, the imputation here is going to replace them. Not like replace them, it's going to do some calculations and take those values and replace all of them. So these are the various ways through which we do imputation. Dummy variables are there. So you have your dummy variables here. And so we are saying that we are going to use some dummy variables using this particular function found in this particular data called train, and then minus the last minus the column which is negative, minus the column 1. Column 1, if you check here, our column 1 is survived. Maybe we didn't have any missing there, so we don't need, so we are taking that out. And then we run that code. And then from there, we can come and then also predict the dummy variables using on this particular column. And then, of course, I don't need to view this again. It is just going to be. So now we are not going to impute. So this is the function we use to impute. So this is going to replace the entire missing values and whatsoever. This is another form. This kind of data replacement is different from what we're using the pipe operator. That was on ordinary data. This one is machine learning, and this is the approach you use in machine learning to be able to do your whatsoever. Okay, there's no time for me. I need to go for. No, I will not view it. So you just run these 2 lines, and then that will work. So now I have the impute data, and then I'm looking for column 6, of course, and then of course now there's most important. Then the next most important thing now. This is now actually where, if we have finished imputing the data, the most important thing now is to split the data into training data and testing data. And in R, what you normally do is to set the seed. The seed is to say that the data set will not exceed this value. You see, 54,000, no, it won't exceed it. So you run that line first before. It's always good. If you don't run it, nothing will happen, but it's always good to set a seed. And so now you use this function to partition the data. You say create data partition, then you go and then mention the name of the data set, which is train. Then you use what survive. Check something here. We are just using only one column, and that column is called survive. And under the survive, we are going to remember it's a probability. So we have to check the number of times we are going to split the data. We are splitting it only once, times 1. And the probability is 0.7, which means 70%. We are taking 70% of the data. And then we say the list is false. That's the syntax. When we run that, we have picked 70% of the data and put it into this variable called indexes. Now when we come, we now say that the Titanic.train data, it means we are now going to look for the train ones. Remember, we have already partitioned 70% of it into this called indexes. So we'll now come and say train, which is the data set, and go there under the rows. We put only the indexes. It will select only the rows of 70%, which has already been selected and packed here. So you put that here. I actually wanted to be doing other examples for all of us to get it. And then to also select the testing data. The testing data is the negative of this one. This is 70%. So negative of this is 30%. It's simple as that. So you run this, that will give you the 30%. So we now have the train data and the testing data sitting separately. That's the work. What is left is nothing. So we now come here, we want to print the probability.table. And we are looking at those who survived. These ones, they are nothing. So we can now check. When we have finished with this place, now we can check originally the people who survived. You can see 61% of the people didn't survive. 38% survived. Now let's come and now look at the training or the Titanic.train survived there, and then we can see the difference. We come and look at the testing, and then we can see the difference. So now we have not built the model yet. We just only try this probability to see whether the model that we are going to build, how is it going to be like? Now, the next thing is to select the model. If you look at the syntax that I gave earlier, the model selection. Here, we are here, choose the model. So, if we come here, we are now going to choose a model and train. Here, so we say train.control. So we have train control, which is actually a function. And then that's where we are going to use to train the model. Okay, so with the rest of the functions that we have here, so I have given the description is already on top there. You leverage on, you just form some kind of a grid here. So you expand the grid. These functions, we should have had some examples for everybody to get it clear, but we didn't. If we can view the grid, it's almost like the same, but it's not the same. So this last part, I will not be able to run it because there's no problem with it, but this is actually where we want to do the actual machine learning. After we've done everything, we now have to make the cluster, and we are making a cluster of 10, and the type is shock. All right, and after that we can register what we can sorry. So after we have done this particular, but this line, I say I don't want to run it because it takes a lot of memory. Let me run it and you see it will take time before it will run, because this is actually where the actual work is going to. It is kind of like iteration, kind of be going back and forth, back and forth. So when we finished, all right, so it has actually worked very fast. But then I thought maybe the internet is good. Now we trained the model using the tenfold that we have created on top here. This part of the tutorial, I will repeat it then when we meet again. From this part, from here, all the way coming down, so that the explanation will be much more clearer. So this one, this particular function, the caret, if you actually know the full meaning of caret, is actually classification and regression training. So we are now going to do the classification and the training of the model. Error in na.default survive. Let me see. There is a missing something somewhere. Error in na.fail.default list. Where? I can't find that. I'm not getting where the error is. Maybe I didn't run the top one here. Yeah. Okay. So let me run this second line and see. Yeah, so that runs properly. But then let me run this C and see something. Okay. So now let me come here and run this line and see. Error in na.fail. I'm not trying to see where the na.fail is. Okay, I'm coming. Let me widen this side. then and this up here, then run this line again and see. But then I need to come around here all over again. Okay, then let me run that line again. There is an error here. Survive equal to approximately this data is equal to Titanic.train. Method is xgb3, and tune grid is equal to tune dot grid. What is the TR control is equal to dot train. I really can't see where the error is. I can't see where the error is coming from.
I think it's talking about the survive that we have there.
Survived here.
And there's a missing value in the survive. The way we say infinity.
Okay, let me see this. There was a day I ran a code. It didn't work. I did all I can. It couldn't work until I just sent it to someone, and the person said that there was a space that I was supposed to have given a space somewhere. The way that thing pained me. Survived. Okay. Or perhaps I have, maybe there's a line I have jumped somewhere. Maybe I have. I really.
We have survived data.
Eh? Yeah.
I mean, a column for survive. Okay.
Yeah. There's a column for survive. Where is it?
But
see,
why are we
specifying
the infinity?
Come again.
Is it, when you were writing the code, I saw some infinity. The tilde sign.
No, the tilde is much more of the the model.
Okay.
Yeah. But I did it.
Again.
I did it and then it worked too. But see, that's the last part. The last part. I don't know whether this will work. Yeah, because that one did not work. Is the other part will not work definitely. The confusion matrix too will not come. That's where we needed to end the confusion matrix. Okay, so I'll leave it here. If I'm able to, if I rectify this issue, then I'll get back to all of you, and then then you get to know. But obviously, what we're going to do, we're going to come out with the actual model now. It would have going to be a tree, and this is the name of the tree. There are several of them: CT tree, XGB tree. Then you specify the kind of tree you wanted. Then after that, this one is just to stop the clustering. It will cluster over and over and over. Here, this was the prediction aspect, which we had spoken earlier. So we just predict. So we're going to be using this classification to be able to predict. It's like I'm beginning to see where the problem came from. I'm dealing with classification and clustering at the same time. Then we come with confusion matrix. Then we'll have our leading diagonal and then the lagging diagonal, and I'll explain what that means. We'll do that for the testing, do that for the train, and then we can compare the two and see what the model performance was. So I'll leave it here, God willing. I will try and then get the other part of what happened and this code didn't run, and then we'll take it from there. Thank you.
Thank you.
Thank you so much. Thank you so much.
You're welcome. When we meet again, we will still try and look at the the next part of machine learning, and that will be unsupervised learning, and then artificial neural network, and that will be is it. Okay, thank you. Like somebody is tired.
I am tired. I'm hungry.
Yeah, me too. I'm going to inside to see if I can cook something. Okay, so we'll leave it here. Bye bye.